So about me, I'm a research engineer at the Barcelona Supercomputing Center. I'm a software guy. I work in compilers, okay, mostly in the HPC space. I've been working on the RISC-V vector extension in LLVM since 2018 in the context of the API process, the European Processor Initiative, the API project that Jean-Marc talked about. And also being involved in the programming models that we develop here at BSc, mostly on OpenMP. So yeah, this talk I want to talk about, yeah, ARM and RISC-V may be rivals in the commercial, but I think there is a lot of synergy and mutual benefit at the technical trenches, especially in the context of open source tools, all the ecosystem that is open source. And in general, the hardware industry so far doesn't seem very fond of open source. I mean, there is momentum building, RISC-V, Open Power. John Davis has mentioned about this. But in the same way, some like traditionally proprietary software companies, they eventually have embraced open source as well. So I mean, the example is Microsoft here. So I want to make the point here in this example, in this presentation, sorry, with the example of the Arm SVE and RISC-V vector extension support that we have in LLVM now, and see how the collaboration between the two organizations and many other, and actually other organizations, is beneficial. So the rivalry may exist in the commercial space, but in the technology side, it's good to collaborate. So very quick overview of Vectorizes. Traditional SIMD have prescribed the size of the vector register. So they are fixed size vector architecture. So I don't know, Intel has SSE, AVX2, AVX512. Each one has different vector registers. Each one has different instructions. This means that you need to create the new, to implement it in the toolchain, in all the stack, in all the software stack, a lot of support for that. So one of the goals when Arm SVE was created, one of them is to address this issue. I mean, it doesn't make any sense to introduce a new ISA just because we're making the vector register longer. I mean, because there is a lot of consequences in terms of a lot of effort and work that just because we are making the vector register longer. Also, Vectorizes are difficult because they require a lot of area, so architects must justify very well every new feature they want to add, every new instruction. Vectorizes also kind of mirror or multiply the equivalent operations in the scalar space. Lots of complexity in terms of a lot of encoding space and instructions, verifications, blah, 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 blah. Lots of issues. So this leads that feeling that, well, when you're working with a vector ISA, there is some missing instruction there that it would be super useful to have. So, I mean, let's focus now on the RISC-V vector extension for a second. So RISC-V actually needed a vector extension. And setting into a fixed size vector extension similar to, I don't know, Intel's, we're having a regressive thing. Also, it would have fit with existing design of the RISC-V ISAs. So RISC-V had to be like Arm SVE in that sense. I mean, the ISA doesn't prescribe the size of the vector register. Also, as I mentioned earlier, the vector ISAs take a lot of code space. So RISC-V could not afford to use so many space, and those trade-offs are also visible in Arm SVE, where you have like destructive instructions, for instance. So we had to encode some of the bits that we usually would put in an instruction into a state of the architecture, okay? Similar to some earlier research project at the University of California, Berkeley. So remember this fact that we have some of the bits cannot be in the instructions. They have to be somewhere else in the state of the CPU. So one of the compilers, I work in compilers. So compilers, the way they work is using this thing called the intermediate representation. And LLVM has its own intermediate representation called LLVM IR, which looks like an assembly with types and all that. And it does have a vector type, but this vector type is fixed size. So it is a good fit for existing architectures that prescribes the size of the vector register, but is not a good fit for Arm SVE, which doesn't do that. And so Arm proposed to the LLVM community a feature called Scalable vector types, which allow you to represent this fact that the vector register can be like can be scaled up to some kind of hardware factor. Okay. Well, it happens that when we started working on RISC-V, we realized that the proposal from Arm is super useful and it fits very well what we need for RISC-V. So and this leads to very nice collaboration because Arm is not alone anymore pushing is not alone anymore pushing the scalable vectors. When this was proposed many years ago, there was some pushback in the LLVM community because this was felt like, hey, this is one odd thing that only ARM needs. But now it's not only ARM, it's also useful for RISC-V. So now it's easier to justify the investment in the change of the technology and the support that LLVM IR needs here in the scalable vector. I mentioned earlier that some of the bits we couldn't put them in the instructions themselves, so they are in the state, in the global state of the architecture. One of these pieces is actually the vector length, which tells how many elements you want to process in every vector instruction, which is, if you look at this, it's very similar to how vector machines used to work in the 70s. So it happens that the researchers from NEC, they proposed a new IR for LLVM because they wanted to generate code for their accelerator, their vector accelerator called NEC Aurora Subasa SX, which also has vector length, but they are fixed size. So here, RISC-V has the two features at the same time. We have vectors whose size is not prescribed by the architecture, so like a bit like Arm SVE, but we also have this vector length. So it happens that this proposal, this new IR, which is called vector predication, it fits very well also RISC-V. So we can use this proposal from NEC. And the fun thing here is that our goal, which we want to use, we BSC, we're pushing for using this vector predication IR in the loop vectorizer of LLVM, so we can use vector length. The nice thing is that the design from the NEC researchers is such that it can also be used for SVE as well. So we from RISC-V, we are pushing, not from RISC-V, from BSC, but interested in the RISC-V use case, we are pushing for vector predication, but eventually at some point, it will be, we plan to use it because it's also usable for SVE, and currently LLVM IR has some limitations that do not allow to make the most of SVE at the moment. So with this proposal, both SVE and also AVX512 will be able to benefit and make the most of their architectures. So quick conclusions. Yeah, the competition is there. Nobody discusses this. Some pieces of infrastructure, it's better that they are open source because they are too big for a single company. So this is a nice natural meeting point for several organizations and several companies at the technical level. And as I mentioned, some solution that initially it felt, you have to think this was 2017 or 2016, I don't remember exactly. This felt like, hey, this odd thing is only useful for SVE. Why we would want to have this in LLVM IR? Well, eventually RISC-V was able to use this, so now there is it makes a lot of sense, and I'm pretty sure there will be more architectures in the future which do not prescribe the size of the vector register, and will be able to use this infrastructure this way that our ARM opened at that moment. And also, again, I mean, this technical proposal made by the NEC engineers and researchers, which is super useful and it fits very well RISC-V, will allow us to generate code in the way we want. And it will also benefit SVE and others. So the conclusion is, yes, there is competition. Yes, there is rivalry. But I think that there are levels where this rivalry cannot exist, and it's much better to have collaboration. So that's it.